Hello everyone, I'm Himanshu Vasnani, Department of Mechanical Engineering. I'm here to discuss you on the subject Material Science, subject code ME207, unit number 4, lecture number 22 in the series, and today's topic are physical and mechanical properties of the metals and some information about cast iron. So, uh, our objective for today is to provide the students with a basic understanding of physical and mechanical properties of the metals and some information on cast iron. That is one of the ferrous metals. And our learning outcome will be for today will be the students have learned the basics of physical and mechanical properties of the metals, cast iron, and students have understood various types of physical and mechanical properties of the metals. So, the physical properties of metals. So, you can see some of the valuable metals I have shown you in this figure, like copper, aluminium, and zinc, and iron, and lead. So, these are some of the examples and how they look like. So, this image will give you a slight idea of the respective metal. The physical properties of the metals include luster, color, size, shape, density, electric, thermal conductivity, and melting point. These are some of the physical properties of the metals. Okay, so I'll discuss some of the properties with you, like corrosion resistance, that it is the material's ability to resist the reaction to move towards a more stable state in its environment, like raw aluminum, silicon, titanium, and their alloys have natural corrosion resistance due to their unreactive layer that quickly forms on their surfaces, and a common alloy for many applications requiring corrosion resistance is stainless steel because this requires corrosion resistance, okay, for many applications. Unlike carbon steel, stainless steel alloys are able to resist surface corrosion when exposed to environments that would normally cause corrosion, okay, including wet, acidic, or heat or high heat. So now the density. Alloys more commonly used in manufacturing have lower density. Okay, so if we go to an example like titanium, so titanium is about half the density of steel and aluminum is about one third. So practically speaking, this means that a part made of steel will weigh approximately three times more than the exact same part made of aluminum. So aluminum is quite lighter. So, however, steel has some other advantages like hardness and strength, and so lower volumes or thicknesses of material can provide the same or better performance comparatively. Then the alloys affects the design, production process, and finishing techniques used to cast parts. So the melting point now, the melting point of a material is defined as the temperature at which it changes from solid to liquid atmospheric pressure. And the melting point can be a major factor in deciding if an alloy will be possible to use for a particular product. And there are different melting points for every material, okay, for every metal also. So different alloys have different melting points ranges, okay, it's as determined by the elements of their chemical makeup. Like for example, an alloy with high percentage of tin, an alloy with a high percentage of tin or aluminium will melt at a much lower temperature than an alloy made of mostly iron and nickel. So there are the variations in the melting points of the materials. Then thermal properties. The thermal properties include heat capacity, thermal conductivity, and thermal expansion. Okay, so in manufacturing, all three properties are important factors in choosing the right alloy. Okay, so you can see in the diagram also the materials are getting hot. Okay, and the heat capacity, also known as specific heat, is the amount of energy needed to change the temperature of a material, and it is a key component of predicting casting solidification. And thermal conductivity, okay, it is defined as the rate at which thermal conductivity is defined as the rate at which the heat can be transported through a material. So, and one thing metals have in common is high thermal conductivity. When heat can travel, it can be transferred from material to material. Okay, in this, so metals have high thermal conductivity. Electrical conductivity is also a different property, but proportionally correlates to thermoconductivity as well. So metals like copper and gold, which are known as good which are known as good electrical conductors, also have good thermal conductivity. Okay, and thermal expansion, then it relates to the way metals expand upon heating and contract upon cooling. Okay, so this property is especially important when designing tooling for metal casting. Okay, so patterns and molds must be larger than its final part in order to account for shrinkage during cooling. Because what happens that during the shrinkage, what happens the size decreases. So whenever they go for the casting process, so the patterns and the molds that they're preparing for the final part to be produced. So the patterns and molds must be larger. Okay, the size must be larger for the final part in order to account for the shrinkage during cooling. Okay, so these were the three general properties, thermal properties like heat capacity, thermal conductivity, and thermal expansion that we should consider. The magnetic properties. So magnetic properties refer to the way in which the materials respond to an applied external magnetic field. Okay, and this magnetic field response can be classified as diamagnetic or paramagnetic or ferromagnetic or antiferromagnetic or ferrimagnetic. In diamagnetic, you can say that it is repelled by the magnetic field. In paramagnetic, you can say it shows no magnetic order. Ferromagnetic means strongest type of magnetism, and ferrimagnetic means weak form of magnetism. So iron is one of the most magnetic metal that is available, and you have also seen in your practical life also that iron is one of the most magnetic metal. And so ferrometals, you get metals that contain iron. Brass, you can also say, like steel, also exhibit degrees of magnetism, especially ferromagnetism. Okay, so ferromagnetism means that strongest type of magnetism. So you can see the magnet in the diagram also on the right hand side. So these are some physical properties of metals like density, melting point, thermoconductivity, and coefficient of expansion at 20 degrees. So they have taken some of the metals on the in the first column. You can see that aluminum, brass, bronze, cast iron, copper. So from this you can easily see that aluminum has density of around 2700 and its melting point is 6600. Aluminum is the one of the most important material that is used in our workshop nowadays for casting processes because for students to practice we normally use aluminum. It has a melting point of 6600, that is good, and thermoconductivity of 220. Then the brass is there, which is having density about more than 2.5 times of aluminium, like 8450, and melting point more than aluminium 950. Okay. Then bronze has a nearby density of 8730, and but the melting point has increased to 1040 degrees centigrade. Then the cast iron, okay, which has a density of around 7250, that is good, and it's at a melting point of around 1300 degrees centigrade. This we have studied in our iron carbon diagram also. Then copper. Copper has density of 8900 and melting point of 1083. So and lead 40 density and melting point 327. You can see the density is very high of lead, but you can see the melting point. The melting point is very less in terms of lead. Okay, in the recent if you compare with the upper example just we have taken. Apart from that, tin also has a very less melting point of around 52 degrees and 32 degrees centigrade. And after that, you have zinc also with that, which has also very low melting point around 419. So the out of the listed metals that you can see, lead, tin, and zinc has very less melting points, less than 500 degrees centigrade. So you can see it's very less. So silver has a good density around 10,500 degrees centigrade, 10,500 density, and melting point of around 960 degrees centigrade. Then steel also has good density, and tungsten you can see one of the finest metals, like having 19,300 as density, and 3410 3,410 degrees centigrade as the melting point. So you can see the range of melting point that tungsten has, and so its applications obviously vary from others. Okay, then cobalt also has a very good melting point at around 1490 degrees centigrade. Molybdenum has also very good melting point around 2650 degrees centigrade. Vanadium also has good melting point 1750 degrees centigrade. So you can see the variation in the melting point of different metals. So this was just for an idea for you. Now the mechanical properties of metals. So the mechanical properties of metals are those which are associated with this ability of the material to resist mechanical forces on load. Okay. So far we studied about the physical properties. Now we're going with the mechanical properties. So these mechanical properties of the metal include like strength, stiffness, elasticity, plasticity, ductility, brittleness, malleability, toughness, resilience, creep, hardness. So like when first we talk about the strength, okay. So we have also discussed this term previously also. So let's get to it. That strength is the ability of a material to resist the externally applied forces without breaking or yielding. Okay. The breaking doesn't happen. You are basically resisting the applied force and not allow the workpiece to break. So this ability of the material is called as strength. Okay. Then the internal resistance offered by a part to an externally applied force is called stress. Obviously, the resistance that we provide by a part to externally applied force it is called as stress. So stiffness. Next, the stiffness. The stiffness is the ability of a material to resist deformation under stress. Okay. Here, the material is resisting deformation under stress. The model of elasticity is the measures of stiffness. So the next is elasticity. Elasticity, we had also discussed this kind of term when we were studying in the starting units, when we were discussing about plastic deformation and elastic deformation. So at that point also, we might have also studied this elasticity property of material, of metals. So elasticity, they say it is a property of a material to gain its original shape after deformation. Okay, when the external forces are removed, like a rubber band. Okay, the if you stretch a rubber band and after a particular time you just remove the external force, then automatically the rubber band will regain its original shape. Okay, after deformation. So elasticity is called elasticity. Springs, for example, may have this facility. Then this property is desirable for materials used in tools and machines. Okay, so you can also say that steel is more elastic than rubber in some few examples. Now plasticity. So it is a property of a material. Plasticity. The plasticity is a property of a material which retains the deformation produced under load permanently. Okay. Now, as the name says, plastic means that whenever you go for this kind of plastic deformation, the changes are permanent. So here also it is saying that in plasticity property, the material retains the deformation. The materials will have to continue the deformation produced under load conditions permanently. The deformation that is done permanently. Okay, so they have said these examples like forging, or you can say stamping or coining or some ornamental work that you do. It is all example of plasticity. Okay. Then we go with the ductility. Then ductility is the property of a material enabling it to be drawn into wire with the application of a tensile force. Now we had also seen in the workshop also when we work with the wires, then they elongate at a particular for a particular length. This is ductility that the material is enabled to be drawn into wires with the application of a tensile force. So ductile material must be both strong and plastic, obviously. Because why plastic? Because it doesn't goes in the backward direction. Once it is stretched, it is stretched, and it's strong because it is holding that you can say tensile force for a long time. So this ductility is usually measured by the terms percentage elongation and percentile reduction in the area. We have also discussed these terms earlier also. The percent elongation means that how much it has elongated within the particular space, and then the area from which it has elongated, then there will be a reduction in the area at that point. So the ductile material commonly used in engineering practice in order of diminishing ductility are mild steel, copper, aluminium, nickel, zinc, tin, and lead. These are some examples of ductile materials. Okay, like aluminium, nickel, copper. Copper we have seen in the wires with, many times. Okay, normally it is used. Aluminum is also used sometimes in wires due to this property. Lead and tin. Okay, then brittleness. The brittleness is the property of a material opposite to ductility. So it is the property of breaking of a material with permanent distortion. Okay, here it is like in ductility, it was not distortion exactly. It was, you can say, uh, we can say the material may get stretched, and after a particular point, it gets broken down. But in brittleness, what happens? It is not getting stretched. It is simply going with the permanent deformation. Okay, or you can say permanent distortion. So the material subjected to tensile loads, a snap of giving any extensive elongation. So you can say the cast iron, one of the ferrous metals, cast iron is a brittle material. Okay. Malleability. Now malleability is a special case of ductility which permits material to be rolled or hammered into thin sheets. Now, this is a special case, we can say, in which the materials or whatever we are using, the metal we are using, they can be rolled or hammered into thin sheets. Okay, so malleable material should be plastic, but it's not essential to be so strong because if it will be strong, it will not be easily hammered. Okay, so the material which is to be malleable, it should be plastic because once deformed, it should be deformed, and it is not essential to be strong. It should be easy and should be workable. The malleable material commonly used in engineering practice are lead and soft steel and wrought iron and copper and aluminium. These are some of the examples of having malleability. Then the toughness. The toughness is a property of a material to resist fracture. Okay, due to the high impact loads like hammer blows. The toughness of the material decreases when it is heated. Okay, now it is measured by the amount of energy that a unit volume of the material has absorbed after being stressed up to the point of fracture. So this property is desirable in parts subjected to shock and impact loads. Okay. So toughness means the thing is tough, so it is resisting the fracture. Okay. When some load impact is there. Okay. This is called toughness. So if you heat the material, automatically the toughness will get decreased. So it is inversely proportional to the heating. So the machinability, then it is the property of a material. Machinability is the property of a material, which refers to a relative case in which a material can be cut or machined easily. The machinability of a material can be measured in a number of ways, such that comparing the tool life for cutting different materials or thus required to remove the material at some given rate or the energy required to remove a unit volume of the material. Okay, it means that you can measure this machinability in a number of ways. Like you can compare the tool life for cutting different materials. Okay, or uh, you can say that the thrust required to remove the material at some given rate, or you can say the energy required to remove a unit volume of the material. So the brass can be easily machined than steel as per the experimental data that is available. So uh, resilience, now the next property. So it is the property of a material to absorb energy and to resist shock and impact loads. Okay, it is the property of a material to absorb energy and to resist shock and impact loads. So it is the amount. It is measured by the amount of energy absorbed per unit volume within elastic limits. So this is essential for spring materials. So spring materials have the property of resilience because they absorb energy, and in this way they resist the shock and impact loads. So which is the main application for springs. Now creep. When a part is subjected to a constant stress at high temperature for a long period of time, it will undergo a slow and permanent deformation called as creep. So this property is considered in designing internal combustion engines, boilers, and turbines. We have also discussed about this creep and different stages of creep, like primary stage, secondary stage, and tertiary stages of creep. And I have discussed about this, the constant stress at constant temperature applied, and how the deformation takes place. Well, the deformation that will be happened after creep will be a kind of a permanent deformation, but it is slow in nature. Okay, this is slow in nature. So in that way, the creep is important, and in designing of various internal combustion engines or boilers, or you can say turbines. Okay, so next then fatigue. Now when a material is subjected to a repeated stress, it fails at stresses below the yield point stress. Okay, such type of failure of a material is known as fatigue, and this fatigue is caused by a means of a progressive crack formation, which is usually fine and of macroscopic size. These properties considered designing in shafts, connecting rods, springs, gears. Okay, so whenever you give a repeated stress, okay, so after a particular point it fails. So this kind of failure is called as fatigue. Okay, uh, why it happens, because if certainly a crack is there, then obviously the crack will become progressive in nature, and it will lead to you can say finally the distortion. So hardness. So hardness is a very important property of the metals and has a wide variety of meaning. Okay. Now it embraces many different properties such as resistance to wear or scratching or deformation and machinability and etc. Okay. So we have discussed about machinability also. So it also means that ability of metal to cut another metal. Okay. And the hardness is usually expressed in numbers which are dependent on the method of making the test. So there are also tests so with which you can determine the hardness. So the hardness of a metal can be determined by the following tests like Brinell's hardness test or Rockwell hardness test, Vickers hardness test or diamond pyramid test or Shore's fluoroscope test. So these are some of the tests with which you can determine the hardness of a material. Okay, and now comes the a small overview of the material testing, because we're talking about such test. So in general, the behavior of the materials under load can determine through standard test, which shows relevant mechanical properties. So normally we have the three types of material deformations, and the corresponding mechanical properties can be summarized like when you have the elastic material properties. So they govern the so-called elastic deformations, where upon removal of the applied loads, the material turns to its original state. Okay, so that is called as a recoverable deformation. Then comes the plastic material properties. Okay, now these plastic material properties, these govern the response of materials in plastic deformation, where upon removal of the applied load, the material does not regain its original shape. Okay, the material does not return to the original state. And finally, it is called as non-recoverable deformation. It is called as non-recoverable deformation. Now, fracture properties, that they define the laws that are associated with the separation of the material, as the name says, fracture in two or more pieces after the application of the same force, application of some force. So in the diagram also you can see that if you apply a tensile force, then what in application is shown, that L naught is shown and L is shown, and initial length is shown, and then the length after experiment is shown by the L, and you have the two forces applied in opposite directions. Okay, you can see the A naught also is shown there. So here that how the tensile forces are applied, the tensile load is applied. Then if you talk about the compressive load, you can see that the force is applied in towards the workpiece, and you can see the change in length. That initially it was L naught, and now it has become L. Okay, and the area also you can see it's A naught is shown. So this is about compressive load. Then the shear load is also shown with you, that how the force is applied and how the shear load is applied on it. Then also the torsion load is also shown there in the diagram. And then this concept of stress and strain, tension and compression. Okay, so to compare specimen of different sizes, the load is calculated per unit area. So you can say that the engineering stress is like force upon A naught area, and the F is the you can say load applied perpendicular to specimen cross section, and A naught is the cross sectional area perpendicular to the force before application of the load. Okay, so here also then engineering strain that we just saw in the previous. So engineering strain they have shown that E is delta L upon L naught into 100 for percentage. So delta L is the change in the length and L naught is the original length. Okay, so and then stress and strain are positive for tensile loads and negative for compressive loads. Okay, so elastic deformation, you can say that it is reversible when the stress is removed, so the material returns to its original dimension it has before loading. And for plastic deformations, you can understand the meaning that if the stress is removed, the material does not return to its original position or original dimension. So look, it does not comes to its previous dimension. Sorry, it does not comes to its previous dimensions. And it's the tensile strength. So how this we can say uh, how it is maintained from you can see how the when the tensile stress is applied, so how the elongation is taking place, and at one point the necking is happen at the center, and after a particular point the fracture happens. Okay, so in this way how the you can say it is applied, and the deformation has taken place if we go beyond the acceptable limits. Okay, then this is the you can say simple diagram showing the tensile properties of yielding, and you can say now we come to the ferrous metals. Okay, so the ferrous metals are those which have iron as the main constituent. Okay, and the ferrous metals commonly used in engineering practice are like cast iron, wrought iron, steel, and alloy steels. Okay, so one of them is the cast iron that we will be discussing right now. So the principal raw materials for all the ferrous metals is pig iron, okay, which is obtained by smelting iron with ore, with coke and limestone in the blast furnace. Okay, so for all the ferrous materials, you can say that the pig iron is the principal raw material, which is obtained by smelting process. So the principal iron cores with the metallic contacts are shown in this one table. Like the iron core is magnetite, and this chemical formula is given Fe2O3. This color is black, and the iron content in is 72%. Okay. Then hematite is Fe3O4, and the color is red, and there's around 70% iron content is there. Then limonite is FeCO3, and it is brown in color, and its iron content is 60 to 65%. Then siderite is Fe2O3 into H2O, and also brown in color, and its iron content is 48% only. So let's discuss now iron cast iron detail. We will go with all the materials one by one, like cast iron, steel, wrought iron. We'll start study all these materials one by one. So let's start the first material, that is cast iron detail now. Now the cast iron is obtained by remelting pig iron with coke and limestone in a furnace known as cupola. Okay. Now it is primarily an alloy of iron and carbon, and this is obtained by remelting the pig iron with coke and limestone. Okay, in a furnace known as cupola. Okay, cupola. Remember the name cupola. So it is primarily an alloy of iron and carbon, and as you know that the carbon content in cast iron is from 1.7% to 4.5%. Some say it's from 2% to 4.5%. So it varies from author to author. It also contains small amounts of silicon and manganese and phosphorus and sulfur. Okay, some amounts of these are for you can say elements are there. Then the carbon in a cast iron is present in either two forms. The first is free carbon or graphite. Okay, the first form is free carbon or graphite. The second is combined form or combined carbon or cementite. Combined carbon or cementite. So two forms are there of cast iron. One is free carbon or graphite, and second is combined carbon or cementite. Now, since the cast iron is a brittle material, means once you throw the material, it will get break down suddenly. Okay, it will lead to sudden distortions. So therefore, it cannot be used in those parts of machines which are subjected to shocks. Okay, so you have to be careful with the application of cast iron because due to its brittleness, you cannot use this material in that parts of machines which are subjected to shocks. So the properties of cast iron, which makes it valuable material for engineering purposes, are its low cost, good casting characteristics, high compressive strength, wear resistance, and excellent machinability. So due to its property of excellent machinability and probably the low cost and good casting, it has its valuable applications also. Okay. Now the compressive strength of cast iron is much greater than the tensile strength. Okay, the compressive strength, you can say when you compress things, the compressive strength is of cast iron is much greater than the tensile strength. So some values are given of the ultimate strength of the cast iron for general knowledge. Like for tensile strength is equals to 500 MPa and the compressive strength is 400 to 1000 MPa. You can see the difference in the tensile and compressive strength. Then you have the shear strength of around 120 MPa. So this is how the values are given for you to understand that the compressive strength of cast iron is much greater than the tensile strength. Okay, so moving ahead through this melting process. Now, ores this consist of non-metallic elements like oxygen or sulfur combined with the wanted metal. Okay. Now, iron is separated from the oxygen in its ore, heating it with carbon monoxide derived from coke. Okay, and a form of carbon made from charcoal, from coal. Sorry, and the limestone is added to keep the impurities liquid so that the iron can separate from them. This is small kind of a smelting process, okay, which you can also see in the diagram also, where you can see the slag or the impurities that floats on top of the iron, and the here the waste gases are used as a fuel in this, okay, and iron ore and coke and limestone, these are loaded into the furnace constantly for the process, and then coke coke, which is a form of carbon made from coal, it burns to carbon monoxide, which releases the iron from the ore, and on the bottom you can see the slag or impurities that are floating on top of the iron. So here you to the smelting process to get the iron. Now the types of cast iron. The We have also discussed earlier also that around grey cast iron and white cast iron are the one of the common names that we have seen regarding the types of cast iron. So the various types of cast iron in use that I discussed are like the first is grey cast iron. So it is ordinary commercial iron having the following compositions like carbon is around 3 to 3.5%. These are all experimental data that they have found out with the help of experiment and researches. Now carbon is around 3 to 3.5% and silicon is around 1 to 2.75% and manganese is around zero point 0.4 to 1.0% and phosphorus is around 0.15 to 1% and sulfur is around 0.02 to 0.15% and the remaining is iron. So you can see that what we have discussed just in the previous slides also, that silicon, manganese, phosphorus, and sulfur, these all are present in cast iron in some or the other amounts. Okay, in minute amount, these four elements are present in it. Okay, and since it's just carbon is present, that's why it is called as cast iron. So the gray color is due to the fact that the carbon is present in the form of free graphite. Okay, so it has low tensile strength, high compressive strength, and no ductility. It has low tensile strength, high compressive strength, and no ductility. So it can be easily machined. A very good property of grey cast iron is that free graphite in the structure act as a lubricant, so it can be easily machined. Okay. So due to this reason, it is very suitable for those parts where sliding action is desired. So the grey iron castings are widely used for machine tool bodies or automotive cylinder blocks or heads or housings or flywheels or pipes and pipe fittings and agriculture implements. So you can see the numerous applications of gray iron castings. Okay, and it is a very good property that the gray cast iron is that the free graphite in the structure will act as a lubricant. So it can be used in those parts where sliding action is desired. So you can see just with such a good property, the applications are vast for gray cast iron. Okay. Now hematite is an ore of iron. So it often forms kidney shaped lumps which may these gives the ore its nickname of kidney ore. Just small information that we give that. Then there are also gray iron castings available, and they hardness and the tensile strength is shown. Okay, so hardness is measured in the form of business hardness number, that is BHN, and the tensile strength is shown as megapascal. And there are some designations given like FG150 is having tensile strength of 150, and the hardness is the in BHN is 130 to 180 BHN. And if there is FG200, FG220, FG260, FG300, FG350, FG400. There are various kinds of different kinds of designations given to the gray cast iron depending upon the hardness and the tensile strength. Okay, so whatever is the application, depending upon the application, you can provide the required material, designated material for that. So according to Indian standard specification, and the gray cast iron is designated by the alphabet FG. Okay, the FG is the technical, you can say, designation of the alphabets, followed by the figure indicating the minimum tensile strength in MPa. Okay, so you can see the designation is shown in FG 150. So it is the FG is the technical, you can say, designated alphabet given to cast iron, gray cast iron, sorry, and the followed by the tensile strength of that particular material. Okay, that is the minimum tensile strength shown there. Okay. Now, for example, FG150 means gray cast iron with 150 MPa, or it has minimum tensile strength. So they have the seven recommended grades of cast iron with the tensile strength and Brittleness hardness number. They are shown in the table. Okay. So now the second thing about the white cast iron, one of the very another name for cast iron. The white cast iron this shows a white fracture and has the following approximate compositions like the carbon. Okay, is around 1.75 to 2.3%. If you compare this with the previous gray cast iron, so grey cast iron was having more carbon in it, and in white cast iron, due to its white factor, due to its you can say structure, it has less carbon in it. So because the grey cast iron shows white fracture, okay. So the following compositions are like this: as a silicon 0.85 to 1.2%, and manganese less than 0.4%, and phosphorus less than 0.2%, and sulfur at less than 0.12%, and remaining is iron. Okay. So the white color is due to the fact that it has no graphite and whole of the carbon is in the form of carbide. Okay, known as cementite, which is the hardest constituents of iron. Now, the grey cast iron was having graphite in it, free graphite in it. And now the thing in white cast iron is that the white color fact that it has no graphite in it. And the whole of the carbon is in the form of carbide, a form of cementite, which is the hardest constituents of iron. So, when the white cast iron is a high tensile strength and low compressive strength. Okay. So since it is hard, it cannot be machined with ordinary cutting tools. So it requires grinding as shaping process. Okay, and then the white cast iron is very produced by casting against metal chills or by regulating analysis. So the chills are used when a hard wear resisting surface is desired for such products such as for car wheels or rolls for crushing grains and jaw crusher blades. So you can see the applications of white cast iron. Okay, it has its own applications. Now chilled cast iron, another kind of cast iron that it is a white cast iron produced by quick cooling of molten iron, and the cooling is generally called chilling, and the cast iron produced is called as chilled cast iron. Okay, so you can see the technical work how it is done. That we going for quick cooling, so it is called chilling, and the produced cast iron is called as chilled cast iron. So all castings are chilled at their outer skin by contact of the molten iron with the cool stand in the mold. So first on most casting, the hardness penetrates to a very small depth, less than 1 mm. So sometimes the casting is chilled intentionally, and sometimes chilled become accidentally to a considerable depth. The intentional chilling carried out by putting inserts of iron and steel chills into the mold. Okay, so they are done intentionally. Chilling is also done, and some are caused due to experimentation also. So when the molten matter comes in contact with the chills, it heats rapidly, is connected away, and the surface hard surface is formed. Okay, the chills are used on any faces or faces of a casting which are required to be hardened to withstand wear and friction. So they have in applications that in which surfaces of a casting which you want to be hard and which should resist friction and wearing, then you can go with the chilled cast iron process for them. Then malted cast iron, that is a product of in between grey and white cast iron in composition, color, and general properties. It is obtained in castings where certain wearing surfaces have been chilled. And then you have the malleable cast iron, and it is, as the name says, that the malleable iron is a cast iron carbon alloy which solidifies in the as cast conditions in a graphite free structure. That is total carbon content is present in the combined form as cementite. Okay, and since it is ductile, so it is ductile and may be bent without breaking or fracturing section. So the tensile strength of the malleable cast iron is usually higher than that of grey cast iron and has its excellent machining qualities. So you can see that cast iron. There are also cast iron also, like malleable cast iron, which has graphite in it, and also it can go for bending process, and you can say without fracturing it will easily bend. Okay, so this is a very good property and quality of malleable cast iron, and obviously it will have a good machining qualities also. So they use some machine parts for which the steel forgings would be too expensive and in which the metal should have a fair degree of accuracy, like hubs of wagon wheels or small fittings in railway rolling stock or brake supports or parts of agricultural machinery, pipe fittings, door hinges, lock. So you can see so much of applications are there for malleable cast iron. Okay, malleable cast iron has so much of applications. Now, there are some you can say methods for this. Okay, but I have to start with the MCQ now, so I'll go with the MCQ first. Okay. Now, the first MCQ for today is that the cast iron is obtained by remelting pig iron with coke. Okay, by remelting pig iron with coke and limestone in a furnace known as cupola. So it is primarily an alloy of iron and carbon. So the answer is A. Okay, iron and carbon. Now, second question: the carbon content in our cast iron is very strong, 1.7% to 4.5%. Okay, the answer is B, 1.7% to 4.5%. Now, in engineering materials, the cast iron contains small amounts of what do you call this? Silicon or manganese or phosphorus or sulfur or all of these. So the answer is E, all of these. We have also seen this kind of small amounts of all these materials in white cast iron and grey cast iron and malleable cast iron. So you can understand that the this all of these are available in the cast iron in small amounts. Okay. When engineering materials, the properties of cast iron which makes it a valuable material for engineering purposes are like its low cost or good casting characteristics or high compressive strength or wear resistance and excellent machinability or all of these. So the answer is E. All of these. All of these properties are important and these make it a valuable material for engineering purpose. Okay. These all are important. In engineering materials, the compressive strength of cast iron is much greater than the tensile strength. We have discussed in the previous slide, and it is true. Okay, the compressive strength was much higher than the tensile strength in case of cast iron. So engineering materials, gray cast iron is an ordinary commercial iron having the following compositions like carbon is 3 to 3.5% or silicon 1 to 2.75%. Then after silicon you have manganese 5.4 to 1.0%, phosphorus from 0.15 to 1%, sulfur from 0.2 to 1.5%, so from zero point 0.02 to 0.15%, and remaining is iron. So it is true in case of grey cast iron. Okay, true. Now in engineering materials, the vast white cast iron has widespread due to the fact that it has no graphite and whole of the carbon is in the form of carbide known as hematite, which is the hardest constituent of iron. So now it is a white cast iron produced by quick cooling of molten iron. And the quick cooling is generally called chilling, and the cast iron is produced called you may call it as chilled cast iron. We have discussed this just few slides ago. It is called as a chilled cast iron. So in engineering materials, the alloy cast iron is produced by adding alloying elements like nickel, chromium, molybdenum, copper, and manganese in sufficient quantities. So it is true. Okay, it is true. You can prove that. Now, in the engineering materials, the nodular or spheroidal graphite cast iron is also called dash. This type of cast iron is obtained by adding small amounts of magnesium like 0.1 to 0.8% to a molten gray iron. Okay, so what do we call this? We call this as ductile cast iron or high strength cast iron. Okay, we call this as ductile cast iron or high strength cast iron. So we have completed with our MCQs, and these are the references which you can refer and increase your knowledge in this subject. The discussion that we did today was more of learning about the properties of the material of metals, and increasing the knowledge about cast iron. That what are the types of cast irons that are available for the industry to use, and how it is produced. So, if you study these books also, you may increase your knowledge in the current topics. So thank you all.